Hello everyone, my name is Zhiqiang Que from Imperial College London, working in the Custom Computing Group. You can also call me Walkie. I'm a fourth-year PhD student under the supervision of Professor Wayne Lu. Today, I'm going to talk about our recent research about optimizing graph neural networks for jet tagging in particle physics on FPGAs. This work is a result of the collaborations with researchers and scientists from CERN and Imperial College London. Jet tagging or jet identification is an important but challenging problem at the CERN Large Hadron Collider, or LHC. It identifies the declays of heavy particles produced at the LHC and distinguishes them from others. More can be found from this reference. This work focuses on JetNet, which is a jet tagging algorithm based on graph neural networks, and it achieves state-of-the-art accuracy. An overview of the JetNet algorithm is shown in this picture. It mainly includes three matrix multiplications, and it also includes three deep neural networks. There are many challenges to run the GNN-based JetNet fast and efficiently on FPGAs. First, the JetNet requires very large amount of computation and has irregular memory access, leading to large inference latency. The second is lacking of a scalable and low latency HS-based JetNet template. To address these challenges, we developed a few optimizations. First, we propose an out-product-based matrix multiplication approach with custom strength reduction. It exploits sparsity patterns and the binary features of the adjacency matrix. It removes all the multiplication operations and largely reduces the number of the addition operations. Thus, it helps to reduce the design latency and improve the design efficiency. It can address the first challenge. Second, a scalable and low latency HS-based JetNet template is created, which enables the generation of low latency FPGA designs. We open source this template with some examples on GitHub. Compared with the JetNet implementation on GPU, our FPGA design is up to 9.5 times faster and achieve 62 times higher power efficiency. I will talk in details in the following slide. This is a diagram of the data flow of the JetNet. And let's focus on the matrix multiplication, especially the MM3 between the matrix E and the transpose of the receiving matrix. First, let's look at the adjacency matrix. To show the idea, here is the example of 4 particles as the input. Please note that a real design will have more particles. The relationship between these particles are defined in 2 matrices. One is the receiving matrix RR, and the other is the sending matrix RS. Both matrices are binary, and each of the column is one hot. Besides, they have a fixed pattern, as shown in this picture. In the JetNet, the matrix E is produced column by column. With the row-based matrix multiplication, it will have lots of irregular memory access. To solve this issue, an out-product-based matrix multiplication for MM3 is proposed, which will fetch the matrix E column by column. This out-product-based matrix multiplication can be further enhanced by the custom strength reduction because the receiving matrix is binary and has a fixed pattern. Each row of the transpose of the receiving matrix is one hot, so only one element is valid. and will involve in the computation, which can largely reduce the amount of the computation and the output memory footprint. The structure pattern in the transpose of receiving matrix also enable the generation of the results column by column. So this is the second column. The detailed implementation is shown in this pseudocode. You can find that the operations of multiplication are unnecessary because the receiving matrix only have binary values. In addition, the memory access of the receiving matrix can be also avoided because the values can be fused into the root index. The reduction of the operations and the iteration numbers are significant. The stress reduction can also be applied to MM1 and MM2, which can remove all the multiplications and additions, as shown in this pseudocode. In addition, this work splits the whole JedaNet model into several sublayers and adopts a layer-wise hardware architecture to map all the sublayers on chip to achieve low latency. Furthermore, all the fully connected layers in the DNs of the JedaNet are unrolled by using as many hardware resources as possible. Finally, we also deployed multiple copies of the FR unit, each processing a vector of the B matrix. Thus, multiple columns can be processed simultaneously to increase the design parallelism and reduce the design initiation interval as well as the latency. A performance model and hardware resource model are designed to do the design space exploration. This picture shows the results of the design space exploration for JedaNet model targeting 50 particles dataset. Each blue dot is an explored design, while the red dots are Pareto designs, forming the Pareto front. This sweet spot shows the explored design candidates, which have a good trade-off between the initiation intervals and the total DSPs on the target FPGAs. In the next few slides, I will talk about evaluation results. With 24-bit fixed point, we achieve the same accuracy at the single position floating point. With our proposed out-product-based matrix multiplication with the custom strength reduction, we can achieve a latency of around 12.5 microseconds, which is reduced from around several milliseconds. With a fine-tuned two-level parallelism, another 6 to 11 times higher performance can be achieved. Finally, the JedaNet can run in less than 2 microseconds, and the initiation interval can be reduced to 9.4 microseconds. With a large JedaNet model, we achieve an initiation interval of about 3 microseconds and a latency about 10 microseconds. Please find more details in our paper. Compared with the GPU implementation, our FPGA design is 9.5 times faster and achieve 62 times higher power efficiency. Our future research includes exploring the use of new FPGA resources and trying to deploy the design in next-generation Collider trigger systems. I will conclude our work in this slide. We propose an out-product-based matrix multiplication approach with customer strength reduction, and an open-source HLS-based template is created for the community. Evaluation results show that our approach and the designs achieve good performance. This is the end of the presentation. Thank you for your listening. If you have any questions, please feel free to email me.